Hello, my name is Edward Verenich. I'm one of the co-authors of this work. I'm affiliated with Clarkson University and the Air Force Research Lab. Our other authors, Alvaro is affiliated with the Air Force Research Lab, and Sarwar and Faraz are affiliated with Clarkson University. The work we're presenting today is FlexServe deployment of PyTorch models as flexible endpoints. First, we'll describe our scenario. So we needed an image classification object detection capability that would classify and detect objects from sensor imagery. Now, this capability needed to work with existing systems. So we needed to plug into an existing environment without introducing any breaking changes to the overall system. Another challenge we faced was that we had rapidly changing target classes, and all of these had possible geometric and photometric variations due to positioning, weather, lighting, etc. And finally, we needed to be able to adjust classification sensitivity dynamically without actually having to retrain and redeploy some of our models. So to motivate why we use PyTorch models, well, there are two reasons. The main one is that we have a large collection of pre-trained PyTorch convolutional neural networks that we use as base models for convolutional feature extraction and other transfer learning. The second reason is that we find that PyTorch's dynamic graph architectures makes the network a little easier to debug as opposed to some of the static computational graph libraries such as TensorFlow. So now we'll talk about some of the challenges that we were facing and how we decided to deal with them. So the first having to do with frequently changing target classes. So in order to deal with that, we use transfer learning techniques. And the reason for that is that for many of the novel classes that we were facing, we really did not have enough label training points to really train these classifiers from scratch. So transfer learning was really useful here. Second one is that a lot of the imagery that comes from different sensors will contain quite a few geometric and photometric variations. And these could be noise, angle, lighting, like I said, weather, and this is due to positioning, the types of sensors, sensor calibration, maybe the sensor moved, things like that. So some of the photometric variations can be dealt with basically regular normalization during the transformation step within the pipeline during inference, but not all of them. And most of the geometric variations are tough to deal with in that step. So to mitigate that problem, we would usually train several different convolutional neural network architectures for the same target class, and would take advantage of different inductive biases of these different architectures. And then finally, our inference service, as mentioned earlier, had to be decoupled from the larger systems that it would interact with. So the natural solution was really to deploy these trained models as RESTful services. So when looking at deployment options, we looked at several things. First, the most obvious one was TensorFlow Serving. It's a very good, popular library for these kinds of deployments. But what we found is that in order to serve the dynamic graph, PyTorch's dynamic graph, we had to go through a two-phase conversion process. We first had to convert it to an intermediate format, ONIX, and then convert that to basically a static computational graph, or basically a TensorFlow model. And what we found that some of the features weren't properly translated. One that we found quite frequently was when we subclassed the NN module of PyTorch to accommodate our Ensemble architecture, which we'll discuss later. And there were other things, but we also found it somewhat difficult to debug, especially after the actual conversion process. The second system we looked at was KF Serving, which is a library for Kubernetes. And Kubernetes is a popular, basically container orchestration system. It can be a good option, but it does require Kubernetes to be installed, and that's not well, more often than not in our case that's too heavy, and sometimes it just can't be done. It also depends on a separate ingress gateway to be installed in Kubernetes, because KF Serving is a serverless library, excuse me. And finally, there's TorchServe, which was released in April of 2020. It was released by Amazon and Facebook, who are major contributors to the PyTorch ecosystem. But it does require Java 8. And again, this is not always possible for us. And as I originally said, it was released after FlexServe. So what's FlexServe then, and what are some of the other capabilities that we have, that we put in there, that we found really helpful? So the first obvious one is really to have minimal dependencies, obviously outside of PyTorch, due to the restrictive and often different host computational environments that we had to operate in. We needed to deploy multiple models behind a single endpoint, which we'll talk about later. We also wanted the ability to for multiple models to share the same GPU resource, essentially run in the same GPU memory up to hardware limits. Then we wanted the inference endpoint, to be flexible in terms of the size of the payload, essentially the batches of images that would come in a single request. And that could range anywhere from 1 to any number that's practically feasible to be transported over HTTP. And finally, we needed a way to adjust endpoint sensitivity dynamically, and through our ensemble methods, we were able to do that to some degree, and we'll talk about that. So this is the high-level view of the FlexServe architecture. What this shows is one, it shows our ensemble architectures, where we have multiple models running within this ensemble module. That in turn interacts with a Flask application, which Flask is an open source Python library to basically expose RESTful endpoints. And that's paired with a gateway interface. In our case, we actually use Gunicorn, which is also open source and frequently used for production deployments of Python-based applications. And both of those run within the same container with all the dependencies. So it is relatively lightweight as opposed to some of the other solutions. And here we get back to the point of having a single endpoint for these requests in case where we have more than one model running within our ensemble. So the first thing we looked at was to deploy these models separately, and then having a capability or a policy at the reverse proxy level. So a reverse proxy would be some kind of a web server, something like Nginx or something, or Apache, and that would sort of distribute the payload to all the models in the ensemble. But we found that was quite a bit slower than actually having these models run within the same ensemble, running through the same request within the endpoint, and having the actual ensemble or essentially the model logic be able to distribute the payload to all of its models. And not only that, this is done within GPU memory, so it's quite fast. So that is the reason for that requirement, and that's how it works right now. On the right of the single container, you see an example consuming client that would send in, an image or a batch of images, and what the client would get back in this case is a JSON response, which would contain each of the models' classification. In this case, the classes are alpha and beta, and so each model would make their prediction, and the FlexServe module would put those together in a single response and send it back to the client. Again, this is this does improve the speed as opposed to having a reverse proxy sort of follow a certain policy to distribute the image payload to different models running in their own Flask endpoints. Not only that, it's a bit more flexible because you don't have to change the actual policy at the reverse proxy level when you have a different number of models. So let's say you went from 5 models to 3 models, and that way the endpoint itself doesn't care about it. So our next feature is our flexible batch size during inference. Now you can pull any number of images within a single request, having one to again to a practical limit for an HTTP request, and then FlexServe will go ahead and predict those classes for each of the images that were sent in, and then it will assemble the response similar to how the ensemble inference works, and that will send it back as a single response to the requesting application. This really helps as far as networking costs and as far as the number of inference calls that are actually triggered by the slower Flask cap. The actual model resides in GPU, so when you do batch several images and those are sent in a single request, it's only a single triggering from the Flask application, and then that following inference of that batch of images is quite fast. So it saves on that end as well. So again, you could see what the format of the response would look like, which is very similar to what we had in our previous slide. The only difference is that each model now has several, so any number of predictions based on how many images were actually sent to it. And finally, our ensemble features allows us to somewhat control the sensitivity of the inference endpoint dynamically. And that means we don't have to actually retrain or redeploy these models. And this is actually used quite a bit, and it has to do with what type of target class we're looking for. It could also depend, which applications and in which surveillance area they're actually trying to perform detection. So sometimes we really care about the number. We'd like to really lower the number of false negatives that we get, and sometimes we just want to filter out as much as we can. So this ensemble model allows us to adjust that sensitivity dynamically. And basically each consuming application can employ their own policy, something like a majority vote or some threshold. Like if, for example, if you want the least number of false negatives, you would adjust the threshold to say when a single model detects something, that basically is a positive detection. Or you can employ some average policy, and then of course within the course of the consuming client lifecycle, they can change their policy as needed. So really to conclude, we found that existing PyTorch model deployment solutions didn't fully meet our requirements to really rapidly train and deploy these capabilities, these inference capabilities. So we designed FlexServe to be a really lightweight, flexible, and an open module, really to be used by the PyTorch user community. Yeah, so the two, as mentioned earlier, two of the major contributors to the ecosystem, to the PyTorch ecosystem, which are Amazon and Facebook, they recognized some of these limitations and released a scalable model deployment library, TorchServe. And as we mentioned earlier, this was released after FlexServe, and it still does require some things that are not always possible to install. Like in this case, it's the Java 8, basically the Java development kit. So FlexServe is still really the simplest solution with very few requirements that can be suitable for a wide range of different applications and can live in different computational environments. So to conclude, if you have any questions, you can contact any of the authors, co-authors listed here. You can also go to our GitHub repository to explore the code, clone it, fork it, whatever you want to do. We'd like to thank the audience. Thank you for your time again, and this concludes our talk. Thank you.